So before I begin, I'd like to thank Professor Panigrahi and the other organizers of this school workshop for giving me this opportunity. I'm a condensed matter theorist by profession, and I'd like to share something that we've done recently, which might be of general interest. I'll come to that very shortly. But before I do, I should thank the two main players in this game, my students, Debraj and Abhirup. They are the ones who are mostly responsible for all the work that I'm going to show you now. And I owe, a debt of gratitude to them. So this work is on the archive, and the archive number is given here. And I should also thank the funders, who've supported my research over the years, as well as many friends and collaborators for various exciting physics discussions. So before I begin, I'd like to, just tell you all that if at any point in time you have any questions, please just stop me and ask. I'll be happy to take your questions. All right. So what I'm going to tell you about today is a story which comes at the intersection of several different fields of physics. Okay. So given that I am a condensed matter physicist, it certainly has a strong feeling from these branches of condensed matter that are called strongly correlated systems and quantum criticality. But there is more. It turns out that this problem that I will bring forward to you today also has strong aspects of the foundations of quantum mechanics and open quantum systems. Okay. And ideas of many particle entanglement are very important here. And certainly the questions that I'm going to ask today are important in this field of quantum technology and as it stands presently. So why are we discussing this? Well, we're in the age of a very strongly technology-driven age. And in some sense, this began a long time ago with the creation of the first transistor back in 1947. And these three gentlemen, Bardeen, Brattain, and Shockley, won the Nobel Prize for this in 1956. But by today, we have extremely powerful chips where instead of having that one big, ugly-looking object called the transistor, scientists and engineers have figured out ways and means by which to put a huge number of them on a small wafer of silicon, which is much smaller than a human thumbnail. Okay, and that is a massive scientific and engineering feat. But even more amazing things are now about to happen, because today we are in the world of quantum technologies, where when we look at things like Josephson junctions and transmons, and you can see here the CEO of Google standing next to his quantum computer, you can see that where this technology is heading is into the age of quantum technologies. Basically, I mean technologies that are governed by the laws of the quantum world, not necessarily the classical. So just a very quick, motivation. The benefits of quantum computers are believed to be, several. They operate under the laws of the quantum world, and for certain tasks, they offer a substantial speed up with respect to classical computers, of course. And on certain tasks, because they exploit the entanglement between a large number of qubits, okay, and the computations of the quantum computer are carried out in parallel. However, these face several challenges as well. These quantum computers are fragile in the sense that they must be protected from the decohering influences of the noisy environments in which they are placed. And furthermore, the outputs of these computations must finally be obtained from measurements that must be timed very carefully so as not to interfere with their processing. So how would this happen? So let's attack this challenge in a simpler system. Let's revisit a very old Gedanken. Professor Usha Devi already mentioned a stalwart Schrödinger. And let's look at this Gedanken that he is famous for. In order to show us how absurd quantum mechanics could be, he actually came up with an entanglement where he says, look, let's take a cat and let's put it inside a box together with a radioactive source in such a way that if the source emits a radiation, then a Geiger counter will sense it and immediately lead to to the emission of poison gas, which will kill the cat. If, on the other hand, the radioactive source does not emit any radiation within a certain given amount of time, then the cat is certainly alive. And what he was trying to point out is that in this rather absurd thought experiment, as long as you are not observing the cat, so imagine that this cat is a cat and radioactive source and the poison gas are all inside a box, an opaque box with a lid on top. And as long as the lid is closed and you're not observing it, as far as you're concerned, the cat is in an equal amplitude superposition of both an alive and a dead state. Okay. So this itself was shocking. And of course, by now, we know that such superpositions are certainly, the heart and soul of quantum mechanics, and they have been verified in various experiments over the years. But let's take this thought experiment and let's make it slightly more realistic in the following sense. This cat is a living organism and must breathe. So let's put it inside an environment which is basically, let's say, a gas of oxygen, of air, basically, oxygenated air, which it can breathe. And according to Zurek, people like Zurek and Zeh, the presence of this environment in the box, along with the cat, will immediately lead to what we call decoherence. What we mean by that is that this environment will entangle with the cat and turn it classical. Okay. At the same time, let's do one more thing. Let's open the lid of the box and let's keep staring at the cat continuously. Okay. Now, what would this observer want to do? By staring at it, the observer would want to project the cat onto one of the states, hopefully alive. Okay. Now, this itself is an extremely interesting story now that we've got into. Not only is the environment around the cat trying to decohere it, the observer also wants to turn it classical by projecting onto one of the classically allowed states of the cat, either alive or dead. So then the overarching question one could ask would be, what is the state of the cat under the competing influences of the environment and the observer? Okay, so that's the question I'd like to ask. So the great ECG Sudarshan, way back in the day, posed another such Gedanken, which in a pithy manner can be, said to be the following, that if you continuously watch a quantum pot, which you're heating up, a pot of, let's say, water, quantum water, and you're heating it up, and if you keep watching it, you'll never allow it to boil. What he basically meant was the following, that if I keep measuring a quantum system continuously, then I will never allow it to be quantum mechanical. I will turn its dynamics classical. So this is what Sudarshan pointed out, and he called this the quantum version of the Zeno effect. Now the question is that at zero temperature, is this, the turning of the quantum pot into a classical one, is this a phase transition or is it a crossover? That's the question, okay? And this question has been revisited recently over the last, let's say, 8 to 10 years in the context of monitored random quantum circuits that are being measured intermittently. Okay, so now what I'm going to do is that I'm going to take a version of that Schrödinger cat question and pose it in the following way. Imagine that instead of the cat, I have a single qubit. Okay, that's this glowing blue sphere that is shown here. Okay, imagine that I have a single qubit, that's a single two-level system or a spin half okay, and it's localized in space. It can't move, okay, so it's not an electron that can move, okay. Now I surround it, which is this red halo. I surround it by an electronic environment. So think of that as a gas of electrons, okay, which is surrounding this qubit. And imagine that it couples to this spin moment, okay, the spin half, through a Heisenberg antiferromagnetic interaction. And it couples locally to that qubit, right? So just like in the Schrödinger cat story, this electronic environment is like the environment for the cat. This will want to decohere the quantumness of that spin half system. At the same time, imagine that I place this qubit, okay, in a local magnetic field. So I couple a local magnetic field to this qubit via a Zeeman term, okay, so that tries to polarize the spin half and make it align along the direction of the applied magnetic field. Think of that as being the equivalent of the observation. And this is a continuous observation because the magnetic field continuously is trying to project the spin half system to polarize it along the direction along which it is pointing. Okay, so what does the Hamiltonian look like? Okay, so the Hamiltonian has three terms. Okay, the first term written here basically corresponds to the kinetic energy of the electrons in the environment. Okay, so this is written in the second quantized notation. Epsilon k corresponds to the kinetic energy or the dispersion, the energy momentum relation. You can think of it as h bar squared k squared by 2m if you wish. And we're summing over all possible momenta that are allowed to these electrons. Okay, now that's the first term. The second term corresponds to the coupling between this impurity spin moment, the spin half, which is localized, this blue sphere, and the spin moment, the local spin moment of the electronic gas that is surrounding it. So that S-env corresponds to this object here. This is basically the local spin moment, okay, the X, Y, and Z of the local spin moment from the gas of electrons that are surrounding this qubit, okay? So, and this J is a antiferromagnetic Heisenberg exchange coupling between the two, okay? And the third term, that's this is a local Zeeman field, B, which is coupled to this impurity spin half, okay, and wants to project it along its direction. Good. So now, if we didn't have this magnetic field, if we switched it off, then if we just had the first two terms, then it's not hard to convince yourself that the ground state of the problem is just a singlet, where the impurity and the local spin of the environment together form a singlet. So if one of them is up, the other is down, and if the first one is down, then the second one must be up. Okay, and there's a 1/√2 factor, and this linear superposition has a minus sign between them. So this is the singlet state. Okay, and as I will point out now, this state is maximally entangled. What I mean by that is that if we integrate out the environment, we will obtain a maximally mixed reduced density matrix for this qubit. So the question that I'm going to ask subsequently, after having shown you that, is the question I'm going to ask is, what happens to this state when I switch on the magnetic field? That's going to be the question I'm going to address today. But before we do that, let's just look at a simple problem of two spins, A and B. Call them Alice and Bob if you want, or whatever. I just like to call them A and B. Two spin halves, degrees of freedom, that are talking to one another through a local Heisenberg antiferromagnetic exchange coupling, whose strength is given by J. Okay, so J is greater than 0. Now, if you think back to the quantum mechanics that you learn, then the ground state is not up A down B or down A up B. Instead, it's the singlet, up down minus down up by √2. Okay, and why is that so? That's because, first of all, remember that this Hamiltonian actually has a rotational symmetry, which is defined on the Bloch sphere of the total spin that I obtain by adding these two and taking their norm. Okay. Now, this SU2 symmetry, that is this rotational symmetry on this Bloch sphere, okay, this SU2 symmetry actually is encoded within the singlet and the triplet zero states of the simple two-spin Hamiltonian. Okay, so this up-down, plus-minus, down-up. So the plus combination is triplet zero. The minus combination is the singlet. Okay, and the 1/√2 is the overall normalization. These two states, I claim, have this SU2 symmetry. What that means is that up, down, and down, up, these two cannot be the eigenstates of this Hamiltonian. Instead, these two are. Okay, and the reason that they happen is because this Hamiltonian actually has the XX and YY terms, which I can write in terms of the raising and lowering operators, SA plus SB minus plus SA minus SB plus. And the action of those terms in this Hamiltonian on these two states instead will lead to the singlet and triplet zero states. Okay. And what I will show you now, so I call these quantum fluctuations. Okay, these are like the 0-point energies within the system. And what I will show you now is that these two states actually have something called entanglement. Now, so let's look at the singlet state. That will be enough to convince you of what's happening. Now, what we should note is that entanglement is the property of a composite system. So I need, two objects between which, or 2 degrees of freedom between which I can look for entanglement. Okay. Now, the recipe is that these two objects, let's call them subsystems, they should be interacting with one another in some way. And the state should not be separable. I should not be able to write it in a way such that I can completely, think of them as broken off from one another. That would be the case in this up-down or this down-up combination. These are the unentangled or separable or direct product states. Instead, the singlet is certainly not. You won't be able to, no matter how hard you try, you won't be able to separate out A and B. But what this means is that if I give you the state of one of the spins, I'm also telling you about the state of the other. Essentially, if I measure the angular momentum of one of the spins, it will also tell you what is the value, the angular momentum value of the others. And indeed, for the singlet, these two results will be anti-correlated. So this entanglement, importantly, is a measure of quantum correlations that can also be non-local. And this is something that Professor Usha Devi was stressing in her lecture just before mine. How would we go ahead and compute? So if we talk about an object like entanglement, a property, how do we compute it? So let's consider the singlet state again, which is the ground state for this antiferromagnetic two-spin Hamiltonian. Okay, let's take this state and let's make a density matrix from it. Okay, which is basically to take the outer product of the ket with the bra, write it down, and trace over all configurations, let's say of the second spin, the B spin, so that we'll get a reduced density matrix just for A. So how would you do that? You take this density matrix operator and you take the matrix elements over both configurations of spin B, up as well as down, and that leaves you with the reduced density matrix rho A, which is just the density matrix of the spin A after having traced over all the possible states of B. And what we can see is that it's a matrix, as it must be, and it looks like this. Half, the diagonal entries are half, and the off-diagonal entries are 0. Okay. Now, we can take this reduced density matrix, and thanks to von Neumann and his genius, we can compute something that he called the entanglement entropy, which is that we can take the elements of this 2x2 matrix and multiply it in a Boltzmann-like formula. Okay. And what you get is log 2. Okay. Now, it turns out that this log 2 is exactly the same number that you'd get whether you traced over B or A. Okay. And indeed, log 2 is the largest amount of entanglement entropy that you can obtain for a single qubit like this, or a single spin half. So even if this spin half, let's say, is talking to many more degrees of freedom, if I trace out all of them, then log 2 is the most I can ever get. I can never get more than log 2. Now, let's go back to that problem of the Kondo spin, the static spin, which is talking to a bath of electrons around it, conduction electrons, and also has a magnetic field, trying to polarize it. So let's first switch off the magnetic field, and let's say the Kondo-Heisenberg exchange has 1. Then, as I pointed out earlier, the ground state that you'd get is the singlet, where the impurity spin and the local spin moment of the conduction bath electrons form a singlet. Now, if I take this state, as I've just shown you, if I trace out the environmental spin, then I would again end up with this reduced density matrix, which is like this half times the identity. Okay, and I've already shown you that the entanglement entropy for this impurity spin will now be the maximal value of log 2. What that is telling us is that this impurity spin has got maximally entangled with this conduction bath electrons in this state. But now, if I write this as a Boltzmann, in terms of Boltzmann weights, then you can see that this maximally mixed state essentially corresponds to the inverse temperature, beta, going to 0, or essentially the effective temperature of the quantum fluctuations that lead to the singlet state can be thought of as infinity. Zurek and Zeh point out that such an eventuality corresponds to what they call the decoherence of the qubit by the electronic environment. So what we're saying here is that the electronic environment and the qubit have got maximally entangled with one another. And if you trace out the environment in the sense of thermodynamics, because let's say the environment has too many degrees of freedom, you can't keep track of them, you trace over them, what you end up with is a maximally mixed density matrix for this spin, which appears to have an effective temperature, which is infinity. Okay. So what we say is that in a statistical sense, this impurity spin has got completely decoherent. Now, this effect is actually seen experimentally and in alloys with magnetic impurities. For instance, in the classic experiments carried out by Madame Sarashik in the 60s, but more newer age avatars have seen this effect by studying the physics of magnetic adatoms that are placed on metallic surfaces, or even taking a two-dimensional electron gas and creating artificial quantum dots on them. So this physics is not just a theorist's imagination. This is actually obtained experimentally and being studied experimentally. Now, if instead of having the magnetic field switched off, let's say the magnetic field is so strong that it wins, it overcomes the effects of that decohering environment. So essentially it wins over the Kondo coupling, the Heisenberg exchange coupling between the conduction bath and the spin. Let's say the magnetic field wins. Then again, you know what the ground state is going to look like. Either you're going to end up with the magnetic field being polarized, okay, and it'll go into direct product state with the state of the environment if the magnetic field is pointing along, let's say, the up direction, if it's positive. And if the magnetic field is negative, then the impurity spin will go into the down direction. So these correspond to decoupled classical states of the qubit that are dictated by the observer field. This essentially corresponds to a projection or a collapse of the state because of the continuous measurement. And here, obviously, given that these are separable states, the entanglement entropy of the impurity spin in this state is 0. So these are unentangled states, and they do not suffer any decoherence because of the environment, because the magnetic field has completely turned them classical by projecting them onto the states that it wanted, the magnetic field wanted. So now the question is, what happens to this ground state if both the magnetic field, the continuous observer, and the Kondo coupling, the decoherence due to the environment, if both of these are non-zero? If both of these compete with one another, what happens? So this this can be given a name, okay? So we can think of this as a frustration of the Kondo coupling due to the magnetic field. And what we'd like to ask is this a phase transition or is this a crossover? Okay. So if we go between the Kondo coupling dominant ground state, the singlet, and this magnetic field dominant, decoupled separable states. Is there a quantum phase transition between them at zero temperature, or is there a smooth crossover? If there is a phase transition, then we would say that this would be projection by emergence. Okay. In order to answer this question, we employed a method called the unitary renormalization group. Now, this method is a method that we invented in my group some years ago, back in 2018, and the first publications came out in 2020. This method basically is a method by which you can take a many-body Hamiltonian and see how it evolves across varying energy scales, just like any renormalization group method does. Alternatively, it can also tell you how the entanglement and many-body correlations that are encoded within the wave functions of the many-body Hamiltonian, okay, also evolve across varying energy scales. So let me spell that out a little more clearly in terms of this diagram. Imagine that you have a quantum circuit, as is shown here, where the dark blue circles given up here are either the degrees of freedom in the input model many-body Hamiltonian that you want to play with, or these are the coefficients of various elements of the tensor product many-body eigenstate that you're playing with. Okay, so these are the inputs that we put in here. Now we put them into an element of the quantum circuit. What is that? It's basically a quantum circuit which comprises of several objects, okay, circuit elements that carry out a many-particle unitary transformation that leads to the decoupling of certain of these input objects, okay? And the ones that are decoupled go to the side, as are shown here, okay? And then the rest of them continue forward, okay, until we keep decoupling them, bit by bit. And then we come finally to an output effective Hamiltonian or an output tensor product state at the end of this set of iteratively applied decoupling many-body or many-particle unitary transformations. So together, each of these objects, when they're placed together in a sequential manner, they comprise a total quantum circuit. Okay, that's what the unitary renormalization group corresponds to. This was shown by us in 2 papers back in 2020. Essentially, these methods are realizations of Feynman's suggestion, okay, that if you want to simulate a quantum matter, strongly interacting quantum matter, then the best way to do it is to conduct or to take a quantum system and use that as a quantum computer, which will then simulate the system that you want to study. Okay. Now the URG is an algorithm that can help you implement this remarkably on a classical computer. You don't need to go to a quantum computer to do it. I mean, certainly I do not have access to a quantum computer, but the algorithm that my students and I have created are able to help us realize these simulations, these quantum simulations, but on classical computers and for finite size prototypes of the quantum systems we wish to study. So how would we do it for the Kondo problem that we are studying here? Well, imagine that what we have here, this is the impurity and its levels. It's few, it has only 4 levels, okay? And these levels here that are given here correspond to the levels of the conduction bath, okay, the electronic bath. And J and V, these could be couplings that make this impurity talk to the electron levels out here, okay? Now the electron levels span from the Fermi energy, we call that the infrared, to far away, we call that the ultraviolet, okay? And the epsilon K correspond to all the kinetic energy for the electrons that can be excited away from the Fermi surface, okay? Good. Now we want the low energy theory. We want to know what happens to this impurity at low energies in the infrared, okay? So we start with a problem where all the degrees of freedom in the conduction bath are initially talking to the impurity. And we carry out these many particle unitary transformations that decouple degrees of freedom in the UV step by step. So how do we do it? We choose energy momentum shells in the conduction bath and apply these unitary transformations and decouple them one shell at a time. And we come in from the unitary from the ultraviolet towards the infrared. The hope is that if the Kondo coupling between the impurity and the conduction bath becomes strong or relevant under the RG flow, then it will lead to the formation of a singlet bound state, which I had mentioned earlier, okay, in the infrared. If the singlet bound state is formed, then we say that since the overall magnetization of that system now vanishes, the singlet has total magnetization 0. Okay, so we say that the conduction bath has carried out a screening of this local moment. This phenomena is called the Kondo screening of the impurity or the local moment. Okay, essentially the iterative application of these unitaries, these many particle unitaries, leads to a kind of an iterative block diagonalization of the many particle Hamiltonian that you start with until you reach an emergent theory in the infrared, okay, which you need to solve. For us, that would correspond to something like the singlet state, okay, and the rest of the electrons would decouple from the singlet. Good. So when we carried out this analysis, what we observed, remarkably, was that we obtained a phase diagram in terms of a control parameter, which essentially just corresponds to the ratio of the continuous observer magnetic field and the decohering Kondo influence of the conduction electrons, okay, the bath. So just this ratio, that's the control parameter. What we observed is that if this control parameter G is less than a certain critical threshold, then under the iterative application of these unitary transformations, the effective coupling just vanishes. What that means is that the Kondo coupling J wins out, the magnetic field essentially disappears from the low energy theory, and you end up with a ground state, which is just that singlet state. Okay, and as I will show you, this corresponds to a kind of a metal in the system. On the other hand, if the control parameter crosses a certain threshold, then the magnetic field effectively wins out, and the Kondo coupling loses out and is, sent to 0. And at that point, the magnetic field wins out, and the ground states you end up with correspond to these polarized local moments, okay, that we discussed earlier. These are the unentangled ground states of the system. Okay. Now, lying between these two at 0 temperature is a critical value of this control parameter that corresponds to a genuine 0 temperature quantum phase transition that separates this symmetry preserved state, the SU2 state, from a symmetry broken polarized local moment states. Okay, so there's a genuine quantum phase transition between these two. That's what we obtained. Now, the overarching question is, what happens exactly at this phase transition? Turns out, as I will show you briefly later on, you end up with a very funny metal out there, and the ground state at that point is very fascinating. So let me just quickly summarize the results that we obtained. What we saw is that in the phase where the Kondo coupling wins out, you end up with the impurity spin being maximally entangled with the conduction bath. It is decohered because of that, decohered and screened. It preserves the SU2 symmetry, and its excitations are gapless in nature. Okay, they're very close to the singlet ground state. On the other hand, when the magnetic field wins out, you end up in an unentangled impurity spin, which is projected by the continuous observer. That's how the symmetry gets broken, and you get polarized local moments. And the excitations of these ground states are gapped instead. Okay. And there's a quantum phase transition, a strict boundary that separates these two. So let me show you some results that we obtained. So the first result I'd like to show you is the following. Imagine just for a moment that we take that artificial 2-spin problem, just two spins that are talking to one another. Okay. If we now, let's say, carry out time dynamics, okay, with this Hamiltonian, with the Heisenberg antiferromagnetic interaction between these two artificial spins, and we start at time 0 from a non-eigenstate of this Hamiltonian, which is just up-down. So we start from a separable state. Then if you carry out a numerical simulation of the time evolution of the state with this Hamiltonian, you see that it oscillates, okay, between the up-down the decoupled state, the up-down separable state, and it varies in time and goes into the singlet, then comes back again to the the decoupled state and goes back to the singlet, and it keeps oscillating like this. Okay, we call this the phenomenon of eigenstate revival. Now contrast this with what we see if you have a more sophisticated version of the same two-spin problem. But here, the second spin is made out of 10 to the 23 electrons, okay, from the conduction bath that form the local spin, okay, the second spin that talks to this impurity. Now, if you carry out this evolution, time evolution, in the presence of a Kondo coupling, you see that this up-down initially separable state goes up. Okay, it's entanglement entropy. Okay, unlike this case here, which kept varying between 0 and the log 2 of the singlet, here it goes up towards log 2 and shows some small oscillations, but in the long time saturates to log 2. So this is where that singlet, the Kondo singlet of the screened impurity, is being formed. This state does not oscillate in the long run. We call this the eigenstate thermalization. Okay. Now let's compare. It's hard to measure entanglement entropy in an experiment. So let's see what happens if you look at an observable, something like the Z component of the spin, the magnetization of the impurity spin. If you measure that for the artificial two-spin problem, you see that it oscillates between up and down, up and down. This is because of the eigenstate revival phenomenon for this finite two-spin problem. But if you have the Kondo version of the problem, where the second spin is formed out of a macroscopic number of electrons, you can see that it starts from the down spin configuration, but very soon oscillates about 0. And in the long time scale, it actually has small oscillations about 0 magnetization. This is the formation of the singlet. Okay, so the orange one actually shows you the formation of the singlet, whereas the blue one doesn't. Okay, contrast this with if you sit on the other hand with a system when the magnetic field has won out in the Kondo problem. There, depending on whether the magnetic field is pointing up or down, no matter whether you start from the up guy, okay, or the down guy, you will either at any point in time evolve only along one of these states. There is no possible quantum, oscillations of the quantum kind between these two. These two are completely boring classical states in that sense. So this corresponds to projection by emergence. Because of the magnetic field being strong enough, it has forcibly, through a quantum phase transition, projected this impurity spin into one of these two classical states. So the last thing that I'd like to tell you about before I finish my talk is what happens exactly at the quantum critical point. So this is the problem that we have been discussing. You have this impurity spin, this green circle, talking to a bath, okay, and I've given it a one-dimensional representation here. The zeroth site refers to the conduction bath electrons, which could be 10 to the 23 number, but which form a local spin, which talks to this impurity spin, okay, through this Kondo coupling. And this red arrow refers to the local Zeeman field, which tries to polarize this impurity set. Okay, and as we saw, the calculation that we carried out shows that there's a quantum phase transition between a singlet phase, where the Kondo coupling wins out, as against a phase in which you have a polarized spin, polarized local moment, in which the magnetic field wins out. Okay, so now let's start with when we are in the metallic phase, where the impurity in the zeroth site form a singlet. Okay, when they form the singlet, okay, ask yourself if you allowed for some electrons to jump from the first site of the conduction bath into the singlet and back out again. Okay, so let's say you minimally disturb that singlet state. Okay, then what would be the density of states, okay, or at the impurity site? Okay, the electronic density of states. You can compute that, and it turns out that what you see is that there's a peak in the density of states exactly at zero energy. Okay. This peak refers to the fact that you had this singlet being formed and the disturbance, okay, that due to electrons jumping in from this first site of the conduction path into this, this singlet state. These excitations cost you minimal energy. These excitations are gapless in nature. That's why you have this peak around zero energy. On the other hand, if you are, and these quasi-particle excitations, by the way, the Hamiltonian for them is reminiscent of what is called the local version of the Fermi liquid. Okay. If you don't know what that means, don't worry about it. But essentially, these excitations look like electrons in nature. However, if you are sitting in the other phase where the magnetic field wins out, where the Kondo breakdown has happened, the screening has broken down because of an extremely strong magnetic field, then it turns out if you disturb that state by trying to force electrons into the impurity from the outside, then you see that the excitations have a gap. There is no density of states at zero energy. Okay, there's a strong gap there. The question is, what happens exactly at the quantum critical point? So what we know is that in one phase you see a strong peak, in the other one you see a gap. What happens exactly at the critical point? The calculation revealed something really fascinating. It turns out that exactly at the quantum critical point, you have two degenerate ground states. And by the way, these are two many-body eigenstates. One of them corresponds to a field-distorted singlet, okay, where the coefficients are actually functions of the field. Okay, so they're not 1 by √2, 1 by √2 anymore. They're something that are different. And one of the polarized states of the impurity, let's say down, down. These two states become degenerate exactly at the quantum critical point. Now, if you try to if you try to send an electron from the from the bath first site into this configuration, because there are two degenerate states there. Okay. Now, if you work in this projected eigenbasis of these two many-body states, it turns out that the Hamiltonian that you get has quantum fluctuations that are in there. And because those quantum fluctuations actually correspond to tunneling between these two degenerate ground states, you keep going back and forth between these two. Now, this completely causes a breakdown of the electronic excitations of the Fermi liquid. And what it means is that the screening cloud actually stretches to the first site of the conduction path. So it's no longer just it's no longer singlet between just the impurity and the zero side of the bath. Even the first site of the bath gets sucked in. That object, now the excitations of that object are no longer simple electron-like. Okay, there's a very fancy breakdown, a mechanism by which the electron-like excitations we saw earlier break down, and instead you have something which we condensed matter theorists called a non-Fermi liquid. So I'm now ready to conclude. What we've observed is that in this system, even if I have a single impurity, a local magnetic moment, a qubit, a single qubit, which is facing the competing influences of decoherence from a bath, an electronic environment, and continuous observation from a magnetic field, then at zero temperature, there exists a quantum phase transition that separates the two phases, one in which the conduction path wins and one in which the magnetic field wins. So it's not guaranteed that just because you're staring at this qubit that you will project it into a classical state. That's not true. The strength of your projection has to be strong enough. Okay. And we call this projection by emergence. This quantum phase transition, okay, in which either the qubit is decohered or it turns classical by continuous observation. The fact that you must have a sharp boundary between these two tells you that projection here must be happening through emergence. The one beautiful puzzle that remains open is exactly at the quantum critical point, we observed that something funny was happening. The ground state is really interesting. In the context of a quantum, in terms of a Schrodinger cat Gedanken, what does this correspond to? And can it be observed experimentally? Thank you. I'm done. I'm ready for any questions.
Yeah, thank you, Professor Siddharth. Any questions?
I have a question. So thank you very much for a very interesting and informative talk. So you have discussed Kondo coupling.
Yes.
In the presence of Kondo coupling, symmetry is preserved while system is coupling
Yes.
with the environment.
Yes.
I mean decoherence. So
Right.
my question is, can we use symmetry properties
Yes.
and then bring to the coherence again, system back to the coherence, and this may help to mitigate quantum errors.
Right. So, okay. So the point is, you want to fight off the environment, right?
Yeah,
So,
I mean, they bring errors there.
right. So that depends on your perspective, of course, right? So from the viewpoint of quantum technologies, I agree with you that an environment is looked upon as a bad thing because they bring about errors, right? Or, they decohere the state. So what you're asking is, can I somehow fight off the influence of the of this environment, right? That's your question, isn't it?
Yes, because we can use topological properties of our material, since you are telling us like symmetry is preserved, so
Right.
we can get some benefits of that.
Yes. So before I answer your question, let me first remind you that the question that I was asking here wasn't quite what you are asking. What I was asking here was something even simpler. That if I have the decohering effects of an environment which is competing with the projective influences of a measuring device, okay, of a continuous measuring device, then who wins? This is not the question that you are asking. Okay, what you're asking is, if I just had a decohering environment, how would I keep the system from decohering? Right? That's the question you were asking. So the question I was asking was slightly more nuanced. I was saying that if you have a decohering environment and I also have a measurement, a continuous measurer, then who wins? Okay, because that's also a fundamental question. And what I showed is that there's a competition between these two, and at zero temperature, there must be a phase transition. Okay, so was that part clear to you?
I'm just asking
No,
whether
so now
we
I'll
can
come to your
use.
question. I just wanted to be clear that you understood what I was trying to say. Was that roughly clear to you?
Yes, it is clear for me.
Okay, fine. So now to come to your question. So in that case, first let's remove this continuous measurement device. Let's forget about the magnetic field. Okay. So then you could ask, is there some way by which I could remove this decoherence? And indeed, there are ways. So one thing that you could do is that you could ask, suppose I looked at a very toy model system of a single qubit. Okay. Suppose I have 10 to the 23 qubits that are all interacting with one another. Okay. And let's say these guys together form some kind of a global entangled state. Imagine something like a global singlet. Okay. Some counterpart of that. Then your question would be, if I took such a state and I acted with it, acted locally on such a state everywhere, but locally with such a decohering environment, then would I be able to fight it off? That's the kind of question that you are asking.
Yeah, this was the second question. Related to the first one. If you increase the number of qubits, what will happen?
Yes. So that is one manifestation, I would put it, right? So what I would say is that there is no overarching answer to your question. That's something that people in the laboratory as well as theorists like myself are asking. So I'm building models as well as simulations to check, and they're of course contending with it in the laboratory. Okay, and they're paying millions of dollars to engineers to try and build even 5 qubits that don't suffer from decoherence, and that is known to be an extreme challenge. So what you are asking is there a simple recipe by which one can get around this? Well, my claim is that there, as far as I know, there is no simple recipe. One way out of this might be to have a densely entangled system, for starters. So if you have a system which is extremely entangled, okay, then would it be possible for this to fight off a decoying environment? So that is a question that we have asked in my group. So my students and I, we put out something on the archive just about a week or 10 days ago. You can take a look at that, where we upgraded the model that I showed you here, to 2 qubits. 2 qubits that are talking to one another through a Heisenberg interaction. Okay, they form a singlet. And then I act locally on one of them with this Kondo coupling and ask, can that Kondo coupling break that original singlet? And what we see is that, again, the Kondo coupling has to be stronger than a certain threshold. If it is not, it cannot break that original singlet. Okay, so again, at least from the viewpoint of a simple toy model, we demonstrated that it is possible under some circumstances to protect a system from the decohering effects of an environment. But please note that I will give this caveat that we are carrying out toy model calculations, and real life experiments in the laboratory have couplings to environments that are much richer and sometimes take us way beyond these simplistic models. Okay, so certainly there is a lot of research that is being done right now, both at the level of model building and studying them theoretically, as well as in the laboratory, to try and see what can work out. We're certainly far from getting a complete answer.
Thank you.